In this problem, we have a saw blade. The angular speed of this 15-inch diameter saw blade is 1500 RPMs. When the power to the saw is turned off, the speed decreases at a constant rate until the blade comes to rest 15 seconds later. Determine the acceleration of the saw tooth on the circumference of the saw blade 5 seconds after the power is turned off. All right, so what do we know? Well, we know the angular speed of the saw blade initially, right? So that's 1500 RPMs. Now that can be represented by theta dot or omega. Now, revolutions per minute is not a good unit to use, so I converted that to radians per second. Right? There are 60 seconds per minute and 2 pi radians per revolution. All right, we know also that the angular speed of the blade at the final time is 0 because it comes to a stop at 15 seconds. So change in time, 15 seconds. And the problem statement says this is reduced at a constant rate. So theta double dot, which is the angular acceleration, or alpha, is constant. And then the radius of the saw blade is 15 inches, or we'll convert that to feet. And we want to know the acceleration of a tooth on the blade at 5 seconds after the power was turned off. All right, so how are we going to attack this problem? Well, the problem did not come with a figure, so it's always good to draw a figure. This gets you familiar with the problem. So here's the figure. We have a saw blade. It's spinning around its center. We have a tooth out here on the circumference of the blade. So it has an angular speed going this way, so the velocity of the tooth is that way, tangent to the path. And it's decreasing its rate, so the acceleration is going in the opposite direction. All right, we want to know what this total acceleration is. So there's going to be a tangential component and a normal component of the acceleration. Now again, one of our tasks is to decide what coordinate system. Well, obviously we know the path of this tooth, so the NT is a natural choice of doing that. All right, so we'll write down the appropriate equation so that we know what to solve for. We'll find the angular acceleration because even though we know it's constant, we don't know what it is. And then using the angular acceleration, we can find the angular velocity at any time. So we want 5 seconds, but we can do it at any time. All right, and we can also, from the angular acceleration, find the tangential acceleration. And then we can use all that information to get what we need to know at 5 seconds. All right, this is a circular motion problem. So we can use the general NT acceleration equation if we want, or we can simplify it using the circular motion equations where V is given by R theta dot, the tangential acceleration is R theta double dot, and the normal acceleration is R theta dot squared. All right, the angular acceleration, it's constant. So the average acceleration is the same as the instantaneous. So if we look at the average acceleration equation, it's change in speed over change in time. So change in speed is theta dot final minus theta dot initial. And we know those. The problem statement gives us that. So final is 0, initial is 50 pi, and the total time is 15 seconds. So we have the angular acceleration. With that, we can find the tangential acceleration because it's equal to R theta double dot. So we just use that equation and we get a value of minus 6.54 feet per second squared. Now, because the angular acceleration is constant, the tangential acceleration is constant as well because R does not change either. All right, then we can go on and get the normal acceleration. The normal acceleration is R theta dot squared, so we need theta dot to do that. Again, we can use the average acceleration equation, but instead of putting final in there, we put theta dot at 5 and 5 seconds. So we get that the angular speed at 5 seconds is 104.72 radians per second, right? All right, so now we can plug that into the normal acceleration equation and get a value. With the normal and tangential acceleration, we have the total acceleration. Now notice how large the normal acceleration is as compared to the tangential. This is often the case when you have a circular motion. The normal acceleration is what is keeping that tooth attached to the blade. So you would expect a large value.